Hello everyone, we are the Box Company. Throughout this presentation you will see at the bottom corner of each slide an indication of who is speaking. Let's begin. Our company's goal is to share a secure and sustainable delivery box with our customers. Our box gives the customer the security and peace of mind to know that their package will arrive when they expect it and it will not be tampered with along the way.
And now introducing the team. We have Jacob doing mechanical design, Tomoki electrical integration, Matthew doing web development, and Nikki materials integration.
With our current situation with COVID-19, we haven't been able to come together in a team to finish our project, but we are certain that this project would work, will be successful, and will be innovative. So today's presentation would focus on 4 key aspects of technology, web application, fabrication, and assembly. After integrating all the electrical components in our box, we have successfully implemented 4 main features of sensor technologies, which is GPS tracking, movement detection, long battery life, and monitoring. Our first technology of GPS tracking uses a GPS module that can track up to 22 satellites and can identify the location of the box worldwide. It can be run in 3 different operation modes of maximum performance, eco, and power save mode. These differences lies in how the tracking engines are used to get the optimum GPS performance and power consumption, depending on the scenario. We have experimented the accuracy of the GPS tracking based on the number of digits of the latitude and longitude, and we concluded to be 1 to 5 meters. The map on the left side shows our experiment when we traveled from one place to another using our GPS tracking. The red dots are all the coordinates of the GPS tracking that were available from the satellite. The box has a battery life of 150 hours, which is equivalent to 6 days, using 3 2000 mAh batteries. The battery life can also be adjusted by user's need, depending on the duration of the shipment, by adding or removing each 2000 mAh batteries. To monitor our battery life, we are using this monitoring module that features a charger module and a fuel gauge module. After integrating all the electrical components together, we have measured the power consumption of our total circuit to be from 172 milliamps to 184 milliamps. When the battery level reaches 20%, this module activates a low battery mode, which will alert the user to charge the box immediately. This is our e-ink shipping label of the box. Not just only we have the shipment details, but we have the battery level shown in the middle top. So here is a block diagram of all the electrical components that we've integrated together, in which all of the information from our sensors will be sent to the web application through the SIM module on the right top corner. Next, our web application lead, Matt, will talk about it in detail.
One of the major components of the box is the online application. The idea behind the web app is to give customers and businesses access to information from any device. For a customer, this is tracking and monitoring the box as it is delivered and receiving a notification when the status is updated. In example, the box is dropped, changes route, or is almost arrived. For a business, they can monitor their whole fleet or an individual box. They can receive updates when something needs their attention, and they can control the box to suit their needs. The first page of the web app is the map view. This is what a business would see when they open up their dashboard. From here, they can filter and search for the information they need. As an example, if you type in the ID of a box in the top search bar, you'll be brought to the location of the box. From there, you can click on the marker and retrieve all the information for that box. This includes the ID, the destination, if it has one, the status, this box is not in use, the recipient and their information, and finally, the box sensor data, which tells us where it is currently located, any forces on the box, and the battery status. Now we can see what it would look like if a box was currently in delivery. as seen by the status chip at the top right. A user could then track the package and receive updates about changes in its status, including flagged incidents. Moving now to the customer's point of view, most of this information is also available to them. They can track their package in real time and receive information notifications when major checkpoints are hit. An approximate delivery time is also calculated. Customers can know exactly when their package should arrive and can have peace of mind knowing that they can track it. Finally, we see what it would look like if a package is successfully delivered. Businesses can then use this information to initiate a pickup sequence. And now I'll pass it on to the wonderful Nikki to talk about materials and assembly.
I'll talk a bit about materials and Jacob will handle the assembly portion. For our material selection, we wanted to select materials that had high impact resistance, but also a lightness and flexibility to keep packages intact, but also their contents safe while keeping light for shipping reasons. We eventually decided on a sandwich setup of carbon fiber reinforced polymer, along with a polymethyl methacrylate, which is a type of acrylic. These materials had a good combination of strength and stiffness, but also a low density, and were within our manufacturing ability as well as within our cost constraints. So on the left we have our carbon fiber, which can be weaved in different ways to provide strength in different directions. It serves as kind of the bread to our sandwich. And then on the right we have our PMMA, which is in spool form for 3D printing and acts as the contents of our sandwich. For prototyping of the inner sandwich layers as well as more complex pieces, we tried PMMA as well as PLA. PMMA had more ideal properties and was generally more flexible and less brittle. However, we had some challenges with delamination, mainly due to printers not being in the right heat conditions. And then later we had problems with prototyping in general due to the COVID situation and facilities closing down. To put together our whole sandwich panel, we would be doing a process called vacuum infusion for the carbon fiber. In this process, you basically take an aluminum sheet, put some carbon fiber layers on top, put the PMMA panel inside, put more carbon fiber layers on top, follow that by aluminum, and then that's all surrounded with a vacuum bag, which is hooked up to a vacuum. The epoxy resin is infused throughout. After the epoxy is cured, the sandwich is removed from the aluminum, and the sandwich panel is completed. This vacuum infusion process has benefits like just a nicer overall finish, but also better rigidity and strength of the materials. Unfortunately, due to the COVID-19 outbreak, a few issues arose, mainly safety in that respirator mask fit testing was cancelled. Respirators are really important to this process so that organic vapors as well as carbon fibers aren't inhaled. As well, facilities to do this whole process were closed, so we were unable to actually do this. On the left, you can see UBC Rocket's carbon fiber process. And now over to Jacob to talk about the assembly.
The main chamber of the box consists of two end panels that can be folded up and in, so the side panels can collapse in and allow the box to be smaller while in storage. The hinges rotate on a 0.5mm steel wire coated in oil that is fed into the hinges. The end panels can be seen folding here. Before the end panels can be folded up, a pin indicated by the red arrow has to be folded up so that the box cannot be collapsed before it is unlocked. When the user disengages the lock through the web app, they are able to open the package as seen here. Now that the package is open, they are able to remove the pin and collapse the box. Shown here is the interior of the electrical bin at the bottom of the box. The blue part here sits on top of a servo motor that engages and disengages the box via the web app. The base of the box houses all of the box's electrical components, including the Arduino, the battery, the PCB board, the servo motor, the SIM module, and the e-ink display. There is no need for a power port, as there is a wireless charger that transmits through the base station of the box. The e-ink display is mounted in the base of the box as seen here and displays critical delivery information. The display only consumes power when the information needs to be updated. Finally, the base station of the box is an optional piece of equipment that can be placed at the recipient's doorstep that provides an extra layer of defense against package thieves. The package is placed on the base and cannot be removed until the lock is disengaged via the web app. The base station also charges the box using the wireless charger integrated. If we were able to keep working on this project, we would fine-tune the PMMA printed plates, as well as do carbon fiber layups on those plates for the most durable box possible. The base station would be made out of a durable material to prevent tampering. The fill density of the prints would also be adjusted to achieve the lightest box possible and still meet strength requirements. Finally, the hinges on the box side panels would be redesigned to be smoother when collapsing the box. And now we will explain the business model. The way our service would work would be to give the customer an option at the checkout for extra package insurance using our box. A fee would be charged, and when the package is en route, the customer could set up an account on our web app. Once the package is open, the customer could schedule a pickup. The box would then be picked up and charged on the truck and returned to the distributors for reuse.
To start with, we'd set up relationships with package distributors such as mail companies or e-commerce sites. We would also create a fleet of pickup trucks to pick up boxes and transport them. And we'd also create a database for data to be stored, processed, and analyzed. Our total budget came to $752.01, with materials taking up about 49% of that and electrical parts coming to 51%. Thanks for listening to our project. We really hope you enjoyed it.